Nice, nice. Yeah, so to answer the question, Zurich, the only place I could find to sit down is the anatomical collection. So that's what you see. But okay. Sorry, there's a bit of background noise because it's literally a corridor. Um, but welcome to a Neuroccino on this Monday morning at 9:30. Good to see you all. And today, Eduardo is very kindly jumping in for me, given that I'm on the road and didn't know if I could make it. So he is going to present the illusion of thinking. Take it away. I'm intrigued.
Yeah, okay, so let me share the screen. Okay, can you see my PDF?
Yes.
Yeah, okay, so welcome to this emergency Neuroccino, I guess. Um, so today's we're gonna discuss a paper that is not from Nature or Science for once. It's not even from a journal, it's a paper published by Apple people. I think this is widely known. It came out last week and it's been already debated quite widely because it's a paper about large language models. And of course, there is a lot of hype around this topic. I thought it might be interesting to discuss this maybe more like in a perspective of science rather than companies. But yeah, so let's take it away. So the paper starts with a brief introduction of what they consider the problem. And as you probably know, there's a bunch of companies that claims that now their large language models or LLMs are now sort of evolving into what they call LRMs, so large reasoning models. Um, and that thanks to mechanisms like long chains of thought, they can exhibit something like general reasoning abilities, which would be like a significant step towards AGI or artificial general intelligence. What they put forward in this paper, however, is that according to the authors, there's like a bunch of critical issues that keep persisting. For example, like the bigger question is of course, whether these models actually reason or simply they leverage, or whether they simply leverage pattern recognition and matching. How these models behave with increasing task complexity, for example, and how do they compare to their equivalent non-thinking version, so like the LLM classic version, so to speak. These newer models are always called like thinking models. So yeah. And so the paper tries to like, address these questions with a slightly new approach, using controllable puzzles rather than standard math problems, which is often the benchmark to test these models. And they do so. I mean, what they say, they say they do it this way because using puzzles have the advantage that complexity can be parameterized more easily than math problems, where the answer is nearly like yes or no, or correct or incorrect. There should be less contamination from training data because a lot of these the benchmarks are widely known and present on the web. And three, they say, okay, using puzzles can actually emphasize the use of algorithmic rules over, like, say, testing final accuracy only. So yeah, they try to basically test this a bunch of models, large language models or large reasoning models, depending on which kind of model they use, using parallels so that they can parametrically vary complexity while maintaining some sort of like same logical structure. Yeah. Okay, I will skip figure one because there is some spoiler there. I will go directly to. Well, this is just basically what I summarized. This introduction. It's very general. You can look into it if you're interested. But yeah, so what is interesting, what they point out about the math problems is basically what you can see in figure 2, this figure. These mathematical problems are the most common benchmark used to test like the performance of these large models. However, what they say, it's like it's not clear whether so you can see, just so that you can understand, we have each column is a different set of mathematical problems. On the y-axis, there is pass at k, which is an index of performance. And then the inference compute budget tokens on the x-axis. And the first row is Claude, and the second row is DeepSeek, with the blue line being the thinking model, and the red dashed line being the classic LLM non-thinking whatever model. So what you can see is that for some mathematical benchmarks, they behave pretty much the same. Claude, DeepSeek, they both reach like a ceiling performance, no matter the thinking or not thinking model. But for some other mathematical benchmarks, there is a discrepancy with the thinking counterpart of the model sort of having higher performance. For example, you can see it's the case for the second column, and it's even more pronounced for the third column. What they say is, well, there's like, according to the authors, there's like a bunch of issues. Like first of all, like the first data set, like there's no difference, so like there's no apparent advantage of the thinking model. There is an advantage for the others, but these are, if I got it correctly, these are more recent data sets, so there is less about this data set on the web, so maybe the model didn't pick them up. And the 25, like the last column seems to be like the hardest benchmark for LLMs or LRMs. But then if you look at the human performance, actually the second set of problems seems harder than the last one. So there is a bit of discrepancy, and it's not really clear whether the models are like the thinking models are actually providing some advantage, or if they're or whether they're not. So what they try to do is to rather set up a set of more like flexibly usable puzzles, which I think most of you know because these are pretty familiar. They use 4 puzzles: the Tower of Hanoi, checker jumping, river crossing, and blocks word. And if you're interested in that, I think you know most of them. There is a short description here. The point is that you have like these configurations of different pieces, and you have to move from configuration A to configuration B, and you have like some restrictions on the move you can make. These problems are fully defined because like we know there's an algorithm, you know, which one is the minimum like number of moves that we can make to solve like each puzzle depending on the pieces that we have. And yeah, we can vary like the complexity of these puzzles. For example, the Tower of Hanoi, you can increase the number of tokens. And the task gets more and more complex. For example, because it needs more and more moves to get solved. And yeah, so yeah, this is what they basically did is to test a bunch of models using these puzzles. This setup shortly. They used basically only they used the most commonly known models. So Claude, DeepSeek, and OpenAI's O series. They run some of the experiments on the like not only the experiments were run also on the OpenAI's O series, because they do not provide access to some internal I think the tokens. Yeah, so Claude and DeepSeek allow access to the thinking tokens, which OpenAI's models do not. So some of the analyses are restricted to DeepSeek and Claude, and some of the others are also including OpenAI's models. But so like let's get to the results. like the first thing they notice, which is basically shown, let's see, maybe this is maybe, yeah, which is shown in this figure 4, is that well, what they say is that most of these models, like LLMs and LRMs together, exhibit three regimes pattern of performance. So, like, again, if you look at this picture, you have like accuracy on the y-axis. Each puzzle is a column. Each row is a model, Claude or DeepSeek, with the respective thinking and unthinking parts. And on the x-axis, you have the complexity of the task. And what you can see is that, or what they say is like, okay, these models seems to exhibit like a three regimes of performance, which I think it's more evident for the Tower of Hanoi, and yeah, a bit also for the other models. But basically, you have like a level of complexity that's very low at the beginning, and in this case, the thinking and non-thinking versions behave pretty much the same, or sometimes, yeah, maybe the non-thinking version even better. And then you have a like middle regime where the thinking version of these models actually exhibit like an increased performance, which you can see here. The blue line tends to go up for longer, while the red line collapses faster. And then you have a level of complexity after which basically the accuracy is zero for both thinking and non-thinking versions. It's pretty much the same like across puzzles. So some puzzles seems to be harder in general. But yeah, this is the general main finding that they push forward. And this is pretty much the same thing that is shown in this other figure. Let's see. In this case, it's the performance average across puzzles and separated for the various regimes. So you can see there is the first regime where the performance is high, even higher for the non-thinking version, which is interesting. So apparently, like simpler models are, well, I mean, that this is often the case, like simpler models are more suited for simpler problems. Then as the task, like as the puzzle gets a bit more complex, there's this advantage of the thinking version. So the blue line is on top. And then there's the complete collapse of the performance. Like no matter the model, performance is basically zero. And yeah, so I mean, this is already something interesting to think about. Let's see, there's a lot of other results. So this is okay, figure 6. What is shown here is basically this analysis focused only on the accuracy, so it also includes the OpenAI's model. You have again accuracy. Okay, each puzzle is a column. You have the accuracy on the y-axis for the first row, and the thinking tokens used during the thinking process on the y-axis on the second row. Each color is a different model, and as you can, what they point, like another finding they point to is that, okay, there is this basically collapse of accuracy after like a certain point of complexity for each puzzle. And this point of collapse seems to align with the point where like the model, even if it's allowed to use more tokens, actually start using either less or stabilize and doesn't use more tokens. I'm not sure, I'm not an expert on this kind of model, so I'm not sure exactly what would be the implication here. But yeah, so I think the model should be allowed to use more tokens with the task getting more complex, so to get a solution, but this actually doesn't happen. So yeah, something to keep in mind. And there's like some more interesting findings specifically focused on the Claude thinking model that you can see here. Because in this case they also explored they tried to explore the intermediate solutions, like not just like the output, but also explore like the intermediate steps explored by the model. to see how these intermediate steps vary as complexity of the puzzle increases. And surprisingly, they point out sometimes the model even keeps exploring the solution space, even if it already has found the correct solution, which is what happens in this part of the, for example, the Tower of Hanoi puzzles. You see that the green line is the range like of correct solutions. And in this case, the fact that in this initial part for simple Tower of Hanoi puzzles, the fact that the red line is on top, it's indicating that the model is keeping exploring solutions even when it already has found a solution that is suitable, which is apparently something that in literature is called overthinking. Well, yeah, I mean, it's just the model is keeping doing stuff even if a solution has been reached. And let's see, so one more result that I want to show you before wrapping up. And yeah, so as you can see in this figure 8, even when the model is provided with in this case, what they show is that even when the model is provided with the instruction to solve the algorithm, the model performance does not improve. So you can see this this is DeepSeek and Claude, the first two columns, Tower of Hanoi puzzles, like the dashed or the solid line, basically the same, doesn't really change, even if you provide instructions to the model. It doesn't improve. This is interesting because, of course, these models are not like code, like they're not supposed to run like code and an algorithm per se, but you would assume that if the model is actually producing some sort of reasoning, they would just follow the algorithm anyway. And second, what they say is that even if they were following the algorithm, that the performance should be different anyway, because finding and validating an algorithm on their own should be harder than just executing a given algorithm. Yeah, another things they point out to is that these kind of models have different performance depending on the task, so the puzzle they provide. So especially for the Tower of Hanoi, the model also generally achieves like a near perfect accuracy when solving the puzzle of the Tower of Hanoi with like n equal 5 disks, which requires at least 31 moves to be solved. Why it fails to solve like puzzles like the river crossing puzzle when you have even a lower number of boats or whatever tokens, which has a solution of like 11 moves or something like that. And this, what they say is like, okay, this is probably like a symptom of the fact that there are way less example of the river crossing puzzle on the internet than the Tower of Hanoi. So these models are probably maybe picking up patterns somewhere found in the web. And yeah, this is basically the last picture. They wrap up. So in short, there seems like they conclude that these thinking models, compared to their like non-thinking versions, they seem to have like this 3 regimes pattern when the performance is very high for both models at the beginning. Then there is an advantage of these thinking models, but then there's a complete collapse of the performance, no matter the kind of model that you use. And they say these results challenge the assumption that these models are actually reasoning and capable of manifesting artificial general intelligence, whatever intelligence is. And then finally, that these models have big troubles in carrying out exact computations, even when provided with the exact algorithm. And basically, differences in the amount of training might also have influenced the performance on puzzles, implying that these models are indeed not actually reasoning, but just efficiently extracting and matching patterns from data, which is interesting. I mean, this is kind of what like the whole like deep learning models things is designed for in general. And yeah, I mean, this paper, if you follow a little bit like what happened like on the web like last week, it's been widely criticized by a lot of people. I've seen mostly two lines of criticism, one of which is basically pointless and ridiculous, which is, oh, Apple is lagging behind, so now they are criticizing others. Um, and the second one, which is maybe like a bit more grounded, but still there's a lot of debate that can be done around it, is that this paper is not actually showing anything that we didn't know about large language models or large reasoning models, whatever you want to call them. At the same time, there's a lot of hype around these models, and if you look at the marketing strategies of most of these companies, well, I mean, they pretty much sponsor these models are, really having like reasoning, like abilities. And for what concerns more like the science side, I think we have already seen there is a lot of hype around these models as well. Like people propose like the use of these models to investigate stuff, like correlating layers of models with behavior or brain data and so on, without properly grounding this kind of assumption. So yeah, this was the paper, and I think we have enough time for a bunch of questions.
Great. Thank you very much. Hands are flying up, and I
And
think Chris
already
was
on.
first.
Okay.
Thank you for presenting a paper in this kind of domain. I'm always hyped by these kind of things. Yeah, what you were saying about the criticism, the problem with this kind of paper is that there is a wild variation of performance depending on how you prompt the model. So how do they control for that? The thing is, the last week I've been experimenting a lot with ChatGPT and Claude actually, to make it run well modify code, but very complex code bases, like thousands of lines of code, and compared to the reasoning it requires to solve the Tower of Hanoi, it's like a completely other level. So it will integrate a bunch of different code bases, think about the solution, find the best solution in its code base, in its like knowledge base, integrate it, test it, and so like I don't know how they can have I don't know how anyone can have a proper a comparable framework to evaluate different models, because it will depend a lot. And if for example, after some research, uh, just the prompts, how you format the prompts for Claude is completely different from how you would format them for ChatGPT. ChatGPT is more like natural language, whereas Claude likes like system prompts, user prompts, and different details. So I really don't see how. So I think that's interesting to do these kind of studies, but at the same time, no one should take these results as what is happening for real in the models, because I don't think they actually know.
Yeah, yeah. So, I mean, first of all, no one really knows beside people working for these companies because most of the what is under the hood is, well, it's a black box. This they point out at the end, and it's like, yeah, I mean, this is just so much you can do about it. For the prompt, that's also a problem. The report, I mean, it's a problem. It's a feature. There's not really much you can do about it. You can decide whether you want to fit your prompt to each model the more appropriate way, or whether you want to keep it constant over all the models you're investigating. So basically, you have to decide what is more suitable for a controlled sort of like experiment. If you go into the appendix, I guess you already know the report, the prompts they used, and the journal structure, and the prompts for each puzzle. I think it's useful to at least these kind of comparisons. They put forward this idea of using puzzles are a sort of new idea. I'm not sure if in this kind of literature this is something that has been already done before. I think it's already something more interesting anyway than using simply math puzzles where you could just like maybe find the solution somewhere online, or maybe where the solution has been included in the training data and then you don't know. Um, but yeah, I mean, really, really hard to
And
know.
also, I was saying in the chat, to me, it looks like something that humans do, like these different regimes that they are showing. So I give the example of like math calculations. If you ask someone to what is 2 plus 4, they will respond instantly with great accuracy. If you start asking like 24 times 15, it will take a little bit more time, and most people will find a decent answer, but it will take some time. But then if you ask like a million, 500, whatever, times another million, then we just give up. And it looks
Yeah,
like the regimes that we see in the reasoning now.
yeah, I mean, this like these models, they do have a huge like slice of stochasticity like built inside. So it's like, do you really want them to ask, oh, let's do this task and please find a solution for me? And do you want them to spit out an algorithm? They're probably not really designed for that, and it's also the fact that they cannot follow the algorithm. Meaning when they are provided with one, it's kind of like showing this feature of these kind of models,
Yeah.
which is a feature. I mean, it is the way they are built. But I think the problem is that like the problem is maybe like I would say it's not necessarily what the models can do. They do what they can do, but maybe the way these models are sold. Like I understand the need to raise like money to keep doing stuff, but sometimes the marketing around these models it's really a bit wild. So if you say that you have a reasoning model, then a reasoning human will be able to implement an algorithm somehow. Also, large multiplications really are really hard. But if you have learned how to multiply numbers at the elementary school, then yeah, you can also multiply numbers with 9 digits. It's gonna take a while, but then you
But
know
you
follow the
couldn't do,
procedure.
most
You're
people
gonna find a
couldn't do
solution.
it in their mind. They would need a notebook.
Sorry.
Most people wouldn't do it in their mind. They would need a notebook.
Yeah, but
And
I would
you
argue
reach
that these
another problem
models
with
they have
these
access
models.
to the whole web. They deal with text, and if you think about writing down notes as simply expanding your memory, then it's like yeah, I mean
It's not only expanding your memory, these models actually benefit a lot from having a notebook. And even if they already have an internal one, having something that can follow, where they can track the reasoning, is actually improving the performance.
yeah, I know, but that is the element of like the stochastic element that does persist. So yeah, I mean yeah, well we could discuss like a whole day on
Yeah.
this. Maybe Lilith before we run out of time.
Yeah, thank you, Eduardo, for presenting this paper. Um, Maybe I missed the main punchline, the evidence for the main their like
The
idea
title.
is that these models are not thinking. What I've seen at the moment is that there are some tasks and the models are performing well when it's simple and they are failing when it is hard. So why is this an evidence for absence of thinking?
Uh, what they point uh, what they point to is that these new versions that are called like thinking versions that imply like some more refined mechanism to like longer chains of thought and so on. They should be like if you look at how they're like often presented, they should start to exhibit this kind of artificial general intelligence, so like beyond like language or beyond like general like using different input from text, images, and whatever. So these models should really be like a new step forward in like the evolution of these models, not just a simple like
And
quantitative.
they do perform better, but
Yeah, they do perform better, but not so much better, and
so is
like
it about the quantity then?
because like if you look at the math, like what they say is like if you look at the mathematical benchmarks, then there's a clear advantage. Nice.
Okay.
But then if you look at puzzles, for example, the collapse of the performance is still pretty like it occurs pretty fast.
Yeah, but it's just
And if this model were thinking or exhibit some sort of general reasoning ability, then you wouldn't expect this kind of drop.
why there might, I mean, if human beings are reasoning and at some point they are failing to perform the task, does it mean that the human beings are not reasoning?
Yes, but you see, I mean, if you provide an human with the algorithm, I think most of the humans are going to be able to follow it. right?
Okay, yes, maybe this
That's
is what
already
I'm
something that
missing.
is very, very far
Wait,
from
wait. So
intelligence.
maybe this is what I'm missing. So even if they provide an algorithm of
Yeah,
algorithm, you mean a solution, and they cannot like follow.
yeah, no, I think like for some of the at a certain point they also provided the instructions, like what you should be doing to solve the puzzle, and the performance doesn't change, which is not, I mean, it's not surprising if you know how these models are roughly built. But again,
Yeah,
then
but
why?
probably it's more like general question then because what do they then consider as reasoning? What it would be
I
for
don't know, like the use of these terms is what drives me mad for this kind of stuff, is that they use these kind of, intelligence, reasoning, thinking, hallucination, overthinking, brain, neural networks. There is nothing that is about brains in these networks. They are like extraordinary machines, but there's nothing that is biologically grounded in these
yeah,
models.
I think the main like
The
issue.
reasoning also like they use these terms because they are fancy, nice terms, and because these models can do a nice imitations of a lot of human behaviors. But then doesn't mean that you're actually replicating those behavior, like you're actually implementing something that is this implemented the same way as we do.
Yeah,
Um,
but I mean, I can imagine that you can reach to the same result with in different ways, whether you are through machine
yeah,
or
yeah, of course you
human
can.
brain. But I think the main question here is uh, what do they think reasoning, and at which point they would say, okay, this model is reasoning. Because at the moment, I see that it's just the task is too complex for the models that there is, but it doesn't mean that they are not reasoning, or if they are reasoning. You see what I mean? It's just what is the reasoning in the first place to then say, okay, this model is
I
reasoning.
don't know, but to be fair,
Uh,
that's not. I couldn't find a definition, but I wouldn't say we don't even know. Like there is not a consensus even for what reasoning is for humans.
yeah, also because there
Like
is
what
huge
like the
debate.
definition of intelligence is has been widely debated for was more than a century, and people still don't know. And a lot of people just gave up on like defining intelligence. So I guess it's like,
Well,
yeah, what bothered me more is just the use of the terminology, because like if you just look at the models and you know what they're doing, then it's nice. They're wonderful tools. They speed up our daily task and so on.
and also, Chris asked in the chat if there is one. No, there is huge debate also between
Oh, yeah, but what do you call reasoning? What do you?
creative thinking, even and associative thinking, and is it the same? Is it not the same? And we still don't know in humans. And how are we going to figure
Yeah,
out?
but would you say, for example, like if you ask most like people that study like linguists or people that studying language, if you ask them, oh, do you think like what ChatGPT is doing is language, they would say, no, really, no, it's just like a fancy imitation of language because that doesn't really match that is similar to language itself in these models. They do produce an output that is really similar to what we would do, but
Yeah, it
yeah.
just I just I think this tower of Hanoi and other tasks that they provided is just were different tasks. I don't feel like they are
I mean, they're fairly similar. They are puzzles where you need to
like
follow some like follow
yeah,
some rules, and you have tokens that you have to move around, and you cannot. Well, there's a
just I
they're
don't
well defined, so there is a mathematical like defined number of minimum moves that you have to make to find a solution. So also you would like this is the kind of like if you really think about intelligence, that would you think okay, once you find the pattern once, then you just apply and that's it. It's gonna take you longer for bigger problems, like more complex problems, that for sure. Like for some big multiplications, you're gonna need a piece of paper to write it down because you cannot do it in your head. I can't do more than 2 digits multiplications in my head, but if you give me a piece of paper, maybe sometime we can do whatever you want. Right. So yeah, I mean, this
Mhm.
is the
Yeah, thank you.
Yeah, I'm not sure we can answer these questions now
Yeah,
in
yeah, no,
40
but
minutes, but
it's
it's just nice
nice
to have a
that
discussion.
they are trying to figure things out like this and also publish some papers. I don't think.
Yeah, I mean, also keep in mind these like papers published by companies that are not peer reviewed, and it's interesting. It's not a bad paper. It's nicely written, but probably
I
there
mean,
are
it's better
shortcomings and
like
stuff.
this than total absence of any information. So
Sorry?
I mean, for me, it's better even if it's not reviewed or something. We just, I mean, we still can read it and
Yeah. No, I think it's nicely written. It's also relatively easy to follow along. But then experts about these models could argue maybe, you know, all the pitfalls and stuff. But
yeah. I think Stefan is trying to stop us, but yeah.
yeah,
Yes,
sorry,
I
just wanted
am.
to ask
Sorry.
whether maybe Anna
I'm
has a
really
question.
enjoying the discussion, but I have to go back to the section room.
Okay, thank you.
Thank you so much for presenting it. This was great. See you next Monday. Bye.